Hi, good evening. Today we're going to look at rotational kinetic energy. Now, before we go fit look at the topic as a whole, we need to first of all know wetin energy be. Then we will come think of wetin kinetic energy be. Then we will also come look at rotational kinetic energy. So we go look at those three terms first before we go dig into what the three as a whole mean and the formula wey we fit take use to solve them, how we go derive those formulas. My name na Moses and I welcome you to another video section with Mosaic Tutors, a place where we dedicate ourselves to teaching mathematics and calculations in Pidgin. So like I talk, we go start from energy. Now energy, as we know, they call am the ability for you to fit do work. So if you fit do work, you need to get energy for you to be able to do that work. Now kinetic energy na the energy wey something possess when e dey in motion. Kinetic energy, I write am as Ke, na the energy wey something get when e dey in motion. That is, when that thing dey move. That energy wey that thing get, we dey call am kinetic energy. Now before we enter rotational energy, first of all, make we look at only kinetic energy as a whole. Now we do kinetic energy when we dey look at object wey physics dey call object in translational motion. In other words, object wey dey move in a straight line from here to here na directly wetin we dey consider when we look at kinetic energy. For example, if a car dey for this point and the car move come to this place, we say this car don use kinetic energy. The energy used here wey e take move from this point A to this point B na wetin we consider as kinetic energy. Now kinetic energy get im own formula, and so the formula for kinetic energy na the half of the mass multiplied by the square of the velocity. We call am half mv square, where m na the mass and v na the velocity. This one we just talk about now na for objects, for particles wey dey move in a straight line, wey dey move from A to B. But no be that one we wan center on today. For today, we dey look at rotational kinetic energy. So no be translational kinetic energy or energy of the a car on motion wey dey go on straight line. No be motion on a straight line, but motion in a rotational axis. Now for us to get the equation for the formula for rotational kinetic energy, the first thing wey we need to do wey be say e go change for here na the velocity. Now for under rotational kinetic energy, this velocity no be the same thing. The velocity wey this car use to move from here to here, wetin we go calculate for straight line, if you wan know the velocity wey e use, you go look at the displacement of this line, then you go divide am by the time wey e take that car to move from here to here. Na that one na im be the normal velocity. But when you look at velocity in rotational motion mean say the thing dey go in circle. So the thing dey go in circle. So if an object wey dey for here before move from here to this place, then this place don change, the radius also don change. So the speed work with the radius of this particular shape, this way wey e dey go to. So which means say our v no go be ordinary v, e go become omega r, or you fit call am wr, but this sign dem dey call am omega. So you fit call am omega r. So you no go get only v for here, v go become omega r. If na for motion wey dey for straight line, you fit use ordinary v, but for motion wey dey go in a circle, for rotational motion, you no go use ordinary v again. The v go become omega r. So the formula remains the same except say you go change V to become omega R. So wetin dis one mean be say for rotational kinetic energy, instead wey I go get V square, I go get half m, V go become omega R, so dis go become omega R square. If I decide to open dis bracket, wetin I go get na half m, omega collect im own square, so omega square, R collect im own square, so dis is R square. So dis na the motion, the formula for rotational kinetic energy. Now dis wey we look na for just one particle, so we dey assume say just one particle dey move in a rotational or in a circular motion. Na the formula wey we go take calculate wetin the rotational kinetic energy be. But what if we get numerous particles wey dey roll at the same time? For example, if I get three necklace, dis is the first necklace, dis is the second necklace, dis is the third necklace. Now the three necklace get different size. So we fit call dis one necklace A, we call dis one necklace B, we call dis one necklace C. Now all of dem, I hold dem with my hand for here like dis. So the three necklace wey I hold, dem dey for my hand. Na my hand wey I take hold dem, na im be dis one. I hold the three necklace at once. I come dey roll the three necklace. When I roll the three necklace, they will go in a kind of circular path, something like this. They will go in a kind of circular path, the three necklaces. Now one thing wey you go notice be say the three necklace dey get different length. Now if the three dey come from this particular point, e mean say the three necklace get the same wetin physics dey call axis of rotation, or e get the same point of rotation. And if e get the same point of rotation, from the center of that point of rotation to the end, to this circumference, we dey call am radius, which means the radius of these three no be the same thing. So this one get different radius, this one get different radius, this one get different radius, because dem be different sizes. So this radius, we fit call am R1, the radius of this one R2, the radius of this one R3. Because na three different particles, surely their mass go also dey different. So the mass of this one go be M1, the mass of this one go be M2, the mass of this one go be M3. But one thing no go change, and that thing na wetin? That thing na the velocity wey dem take dey move, which is this angular velocity. The angular velocity na the same because I dey hold the three at once, so I dey roll the three of them with the same speed. In other words, e no go change the velocity. The velocity go be the same thing throughout. So I fit use the velocity of the three of them as omega. Now these three different necklace, they go get three different rotational kinetic energy. So make we look at each of the necklace. For necklace A, if we look at our formula for rotational kinetic energy, we say na half m omega square r square. But we get different r and we get different m. So for the A part, R1 and M1 na im be the radius and the mass. So we go write the formula half m, no be just m1, because e get im own specific number. So this is half m1, the omega no change because na the same thing for everything. So omega square, the r na r1, so r1 square. The wetin dey here na the same thing wey dey here. I just put their subscript, this number wey dey for down, so that we go take identify them. This one na for A. Now for B, you go get half, the m na m2, so half m2, omega na the same thing, so omega square, then you get r2, so r2 square, because we squared the r. Now for the third one, which is C, you go get half m3, the third mass, omega na the same thing, so omega square r3 square. So if you look here, everything, the rotational kinetic energy for this particular three necklace, now we don identify for here already. But what if they come say make you find the total rotational kinetic energy of the three necklace at once? E dey tedious make you begin dey do one 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 like this, one after the other. So we fit just add all of them together. So you fit add A, B and C. When you add A, B and C, you go dey get total rotational kinetic energy go give you the first one, half m1 omega square r1 square plus half m2 omega square r2 square plus half m3 omega square r3 square. So we dey add these three together, na wetin dey for here. So now if we look through, we go see say some things dey repetitive, some things dey here wey also dey here, wey also dey here. For example, half dey here, half dey here, half dey here. Omega square dey here, omega square dey here, omega square dey here. But the mass no be the same because this one na m1, this one na m2, so the mass difference one na m3. The radius no also be the same, this one na r1, this one na r2, this one na r3. So na only two things na dey the same for there. So we fit put those two things together, do wetin mathematics dey call factorize. So the total rotational kinetic energy go become, you pick half from all of them, you pick omega square from all of them. All of them get half, all of them get omega square. So you pick all of them, then you open a bracket, you take the remaining one. Wetin remain for here? When you pick half and omega square, e remain m1 r1 square plus here remain m2 r2 square plus here remain m3 r3 square close bracket. So na wetin remain for here be this. Now this means say you dey add the different values of this mass and radius. So instead of having this, you fit just write the summation of the mass and radius. So your total rotational kinetic energy fit become half omega square the summation of m r square. So summation of m r square means all the value of m wey you get and all the value of r wey you get, add all of them together, then you add. So this go become our formula for the total rotational. Now, having known the rotational kinetic energy of a particle and the total rotational kinetic energy of different particles, the next thing wey we no fit escape or wey we no fit keep na the moment of inertia. The moment of inertia. Now you fit describe the moment of inertia for English say the property of an object that causes it to resist a change in its angular velocity. In other words, that moment of inertia na that property wey go make e no get angular velocity. That is, the angular velocity no go change. In other words, there will not be any rise in the angular velocity, which means you fit ignore the angular velocity because e no dey important. The angular velocity no dey important. Now another formula or another way of defining it, you fit define am as the sum of products obtained by multiplying the mass of each particle by the square of its distance from the axis of rotation. This one just simply mean say you go just multiply the mass of that particle by the square of the distance or the square of the radius. So from this definition, we see say the moment of inertia written as I dey equals to the mass multiply by the square of the distance from the axis of rotation. Whenever you hear axis of rotation, e mean say na the center of a circle, and the distance from the center of the circle to any part of the circumference na the radius. Na why we dey denote them by writing arrow. So our moment of inertia formula now go come be equals to m(r) square. m(r) square. You go look say dis formula dey kind of similar to rotational kinetic energy. The only thing wey dey miss for here na the angular velocity, which is that W wey we write. Now that take us back to the definition. Definition talk say na the property of that object wey go make am no change in angular velocity. In other words, the angular velocity no dey important because e no dey change, nothing dey touch am. So that is not important. Wetin dey important na the mass of that particle and the distance from the axis of rotation, which is the radius. So you get your moment of inertia as mass multiplied by the square of the radius, which is m(r) square. Now e get relationship wey dey between rotational kinetic energy and the moment of inertia, because you can interchange them. Some questions actually mix the two of them, so you need to mix the two of them together in some of the formulas to calculate your either moment of inertia or rotational kinetic energy. Now if we go back to our formula for rotational kinetic energy, we talk say rotational kinetic energy dey equal to half omega square m(r) square. Dis na the formula for rotational kinetic energy. Now we talk say for moment of inertia, the only thing wey no dey there na dis omega and dis half wey we dey multiply, which means dis one dey here. If you look here, you go see m(r) square. If you also look here, you go see m(r) square, which means we fit substitute, we fit remove m(r) square, put I. Since we say m(r) square and I na the same thing, we fit remove m(r) square, put I for inside dis formula, and then the formula go also fit stand on its own, which means you fit write rotational kinetic energy as being half I omega square. Dis I here na im denote for dis. Dis dey important because in some question dem fit no give you the mass or the radius, dem fit give you only the moment of inertia of the particle, and dem give you the angular velocity, and dem say find the rotational kinetic energy. You fit either decide to find I first or use dis particular formula. So dis na the relationship wey exist between the rotational kinetic energy of a particle and the moment of inertia of that particle. Watch out for our next video where we go look at the moment of inertia of different particles, of particles with different shapes. Thank you very much for watching, and we'll see you next time.